As the internet has shown, most locks suck. Experts indicate that 90% of US door locks are susceptible to bumping. Someone with a bump key, or one of these, could walk right through my front door, and probably yours too. The problem for consumers is lock companies have given up on security. They are technological dinosaurs, grinding along with a brand name and century-old designs. I am sick of this stagnation and lack of interest in security. And if they're not going to do anything, I will. That's why I'm on a mission to make an unpickable lock. In the last video, I designed and manufactured this lock. Now I'm going to try to pick it open using your suggestions. I'll be attacking the lock mainly in this jig, which includes a deadbolt. I think it's important to have the lock in a realistic configuration so that its interaction with other elements may also be tested for security vulnerabilities. Thank you for your suggestions. I've reviewed the comments on the last two videos, and I'll be attacking the lock in 4 different ways: picking, bypass, kinetic, and decoding. Before I begin, let's get a quick refresher on how to pick a lock. Pin and tumbler locks are made up of a core and a shell with key and driver pins that prevent the rotation of the core unless the correct key is inserted. Lock picking exploits the imperfect nature of the world we live in. Small variations in these elements change how they interact from lock to lock and pin to pin. These imperfections in components allow for just a single driver pin to be pinched between the core and the shell. This pinched pin is called the binding pin. Feeling each of the pin stacks, this pin can be found and lifted until we hear a click. This process is repeated until the lock opens. Let's see what happens when I try to pick the lock. You can see the lock begins to turn, but stops. Let's take a look at why this is and a different potential picking attack that I got in the comments. This design works by separating the setting from the testing. When the pins are being set, they aren't tested, and when they're being tested, they cannot be changed. The suggested attack vector involves attaching the core to the midcore in some way, either with glue or wedging. Then, with the two attached, pick the lock as normal, as it would behave much like a regular pin and tumbler lock. If not for one feature, the watchdog pin. This pin sits at the rear of the lock and rests on a cam surface with its own driver pin. You can see, with the core attached to the midcore, the entire system gets gummed up, and you're not going to be able to start picking the pins at this interface because this driver pin is always going to bind. In normal operation, the core is free to rotate and lifts the watchdog and driver pin as it does so. The interface between the midcore and shell is now free to rotate, and testing can occur. If successful, the lock will open. If you want to see more specifics about the individual components of this lock, go take a look at my last video where I talked in depth about the design. Bypass attacks are by far the scariest from a security design perspective. They pose the question, not what was the lock designed to do, but what can it do? The mechanics of the lock system are manipulated in some way that they're not intended to operate, typically circumventing the main function of the lock. This category is by far the most varied, as each lock system needs to be independently investigated. Common attacks in this category are bypass drivers and comb picks. Bypass tools directly attack the locking mechanism in some manner. Padlocks seem to be the most susceptible to this attack vector. That said, one opportunity for a bypass attack presents itself with this lock. Since the lock can readily drop into a false gate, the core can rotate slightly. If the clocking of the tailpiece and the deadbolt wasn't correctly designed, it may be possible for that small rotation to disengage the lock on the deadbolt here, allowing it to be walked back. Let me show you what that would look like. This is how the lockpicking lawyer defeated one of Stuff Made Here's locks. Comb picking, also known as an overlifting attack, works by lifting the key pins above the shear line. With the pins completely out of the way, the lock can easily be opened. Just as easy as the lock can be opened, the design can be changed to thwart this attack. The max travel of the pin stack can be limited, so only especially poor designs are susceptible to this attack. As far as this design goes, let's look at what happens when you try to overlift the pins. As discussed, overlifting attacks typically require the stack to be lifted above the core. While I don't think it's typically possible to lift the pins this high, you can see that even if you did, it wouldn't be sufficient. You would need to overlift above the midcore, which I am certain is impossible. Decoding is a type of attack where the pinning of the lock is determined without the use of the key. That is, the attacker determines the shape of the key by manipulating the lock itself. The most common type of decoding attack is called impressioning. In this attack, a blank key is inserted and torqued, leaving marks on the key. The resulting impressions left by the binding pins are then filed away. Over time, the repeated process creates a working key. In this design, since the pins that bind are separated from the key, they can't leave any impressions, preventing the attack. While impressioning won't work, let's take a step back and look at this lock through the lens of a general decoding attack. As an attacker, we don't know what the key looks like. Take another look at this lock. Imagine we raise each pin stack until we hit the hard stop. Since the height of the pin stack is driven by the length of the driver pin, we can calculate the height and make the corresponding key. This attack does in fact require a design change and highlights the importance of this activity. Fortunately, the change I've come up with is pretty small. What we need to do is take inversely long master pins and place them on top of the driver pins, making all of the pin stacks the same height. Kinetic attacks were by far the most suggested attack to try. As the name suggests, kinetic attacks involve applying some motion to the lock to unlock it. Types of attacks include zipping, raking, bumping, vibrating, and impact attacks. Raking attacks involve bouncing pins around the shear line. The mechanics are largely the same as single pin picking, as each pin binds in quick succession. The outcome is the same though, and the lock is immediately put into a false set. Zipping, bumping, and vibrating rely on high-speed momentum transfer and subsequent movement. While light tension is applied, a tool of some kind strikes the key pins, transferring momentum. The pins bounce up, and the driver pin gets set at the shear line. All of this happens extremely fast, on the order of several milliseconds. I appreciate your confidence in the comments about the effectiveness of these attacks. For many, many, many locks, these high-velocity attacks are extremely devastating. Attempting this attack on the lock once again results in it quickly dropping into a false set. I also don't think it's possible to rotate the core fast enough to tension the upper shear line while the pins are still in motion. It would take at minimum several tens of milliseconds to rotate that far. Impact attacks involve hammering or tapping the outside of the lock to manipulate internal components, and stands as one of the most promising attacks we're going to try today. As we saw when discussing overlifting attacks, there's no time where the two shear lines line up except for when the pin is raised the correct height. However, if we raise the pins to the max height, you can see that that would leave only a small distance the master pin would have to jump in order to clear the upper shear line. All right, fully pinned up. Let's push all those pins up. And I don't have great access, so I'm just gonna hit the face of the core that I can see. I'll start there and see how that goes. I feel like the plastic is cheating, so I've pulled the lock out a little bit. I mean, there's always gonna be some kind of, no matter how it's mounted, there's always gonna be some surface available for you to strike. So we'll see if I can pop this thing open. And we have an open. That attack was way more effective than I was expecting. I do want to shout out Alexander J for commenting multiple times discussing kinetic attacks, so good job. As you might expect, a design change is required. And once again, it's really important to keep the design simple so it's easy to produce. Two pin stacks will be changed slightly. The number 1 key pin will be swapped with the number 2 key pin, and the number of wafers will be reduced by 1. The overall height of the stack remains the same. However, it limits the maximum travel of the stack and doubles the height the driver pins now must jump. In my testing, I cleared all main pin stacks except for the impact arrest stack. And while I've been able to open it, it took considerable effort. It should be noted I performed my testing without the addition of the topper pins from the decoding design change. These pins will add preload to the springs, increasing their force. With the addition of a second impact arrest pin, I have been unable to get the lock to open. The possibility of removing an additional wafer is an option I'm open to. Placing the pins towards the back of the lock and the usage of some kind of security pin should also increase the effectiveness. The addition is not without downsides, of course. Usage of this pin stack reduces valid bidding, specifically cuts 1 and 2. Intelligent placement of these pins will allow for most key cuts to remain valid. Let me know what you think of these ideas in the comments below. I also had several comments discussing destructive attacks. These suggestions of how to destroy the door, latch, or adjacent window indicate to me that I must be on the right track, and I hope to see the number of these suggestions grow in the future. There are two main reasons we want to push attackers towards these destructive attacks. First of all, destructive attacks are loud. Imagine you're asleep in bed. Would you rather be woken up by someone kicking down your door or not? And second, destructive attacks are overt, meaning it'll be readily apparent someone is gaining or has gained access because of the damage. This also means that it'll be easier to file your insurance claim, unfortunately. If lock companies would listen, I would beg them to perform an exercise like this. Listen to suggestions. Think like an attacker. Make small changes with a big impact. Actually try to improve your product. I want to make sure this project provides value. So if you think it's worth my time to continue to work on this lock with the intention to bring it to market, please like the pinned comment down below. Otherwise, thanks for watching.